Okay, let's begin. So today I will talk about neutron scattering and critical phenomenon. This will be the first part of 2 lectures. Again, my name is Young Lee. I'm a professor in the Department of Physics at MIT. And as an outline of the talk, critical phenomena goes hand in hand with phase transitions. So let me go over some general introduction to critical phenomena and phase transitions. So some of the key concepts will be mean field theory to describe the transition. I'll define some terms like order parameters, etc. And then discuss the critical behavior and some important parameters that describe these transitions, the critical exponents. And there's this nice idea that's quite powerful in condensed matter physics that very different physical systems can have very similar critical behavior if a certain set of parameters are similar, such as dimensionality or symmetry of order parameter, which I'll get into, and they can fall into similar universality classes. And it turns out that neutron scattering has played a really important role in our understanding of critical phenomenon. And I will go to some older papers that are kind of a case study of how to study phase transitions. And in particular, let me focus on phase transition in a two-dimensional magnet. And a quite famous one is K2NiF4, potassium nickel fluoride. And this will be also a way to talk about some neutron scattering techniques to measure some observables related to the critical behavior, and in particular what's called the static structure factor using the quasi-elastic approximation. Okay, now just as a big picture overview of phase transitions, so let's consider phase transitions that occur as a function of temperature and at high temperatures, say in a liquid where you have a collection of interacting atoms, or at high temperatures in a magnet where you have a collection of interacting magnetic moments. When the temperature is high, the thermal energy essentially jostles these degrees of freedom, and they're essentially random to have a high entropy state in equilibrium. As you cool down, and turns out there is a transition temperature, which will denote Tc, then you will enter into a new phase. And in the case of the collection of atoms, you would form some crystal. In a collection of magnetic moments, you form some ordered magnet, such as a ferromagnet. And our current theoretical understanding, the paradigm that we use, is that when you cool into a new phase, you break symmetry. So in the case of the top here for the crystal, you break translational symmetry in that there are now special wave vectors to bring you from one atom to the next atom. And in the case of the magnetic moments, you break spin rotational symmetry. So there's a particular direction in spin space which the moments want to be polarized along. So this brings in the idea of having broken symmetries and having an order parameter that describes the phase that you're entering. And the general paradigm is sometimes called Landau theory. So that brings up this idea of an order parameter. And this is part of the answer to the question how to distinguish different phases. And the way to distinguish different phases in these conventional phase transitions is with an order parameter, which is just a thermodynamic function that is different in each phase. And in fact, typically at high temperatures above Tc, this order parameter has a value of 0, and then below Tc, it becomes non-zero. So that's a clearly different value for that function in each phase. So for the ferromagnet, we've already, you could probably have guessed what the order parameter is. We can just take the magnetization And we know that the magnetization can depend on temperature and field, so we'll just take the H goes into 0 limit. And this magnetization is just, you can think of the thermal average of summing all the moments. For the antiferromagnet, we have a very similar idea for the order parameter. However, you cannot use the uniform magnetization, but you want to consider the magnetization of one of the sublattices, because when you add the magnetization of all the sublattices, that will sum to 0, so clearly the uniform magnetization isn't a good order parameter, but the sublattice magnetization is. Another way to think about it is you can write the order parameter as the sum where you have this -1 to the I power, so that alternates depending on what sublattice you are on, and this gives you the staggered moment instead of the uniform moment. So for the discussion of phase transitions, I'm going to primarily talk about magnets such as these, but phase transitions in critical phenomena are more general. So let's consider the way order parameters can change with temperature. So as I said, above Tc, the order parameter is 0, and then below Tc, it becomes non-zero, but there are different ways that it can become non-zero. And in this first cartoon, so temperature is on the x-axis, the order parameter m is on the y-axis. Well, there might be a very sharp or discontinuous jump as a function of temperature for this order parameter. And when this discontinuous type of transition occurs, we say that's a first order phase transition. There are some consequences or things that go hand in hand with that. You get hysteretic behavior. For example, on warming and cooling, you might get shifts in where this phase transition occurs, and there's a latent heat associated with this phase transition. Another way that the phase transition can occur is as a function of temperature. As you cool down, you get this more gradual onset of the order parameter becoming non-zero. And this is a continuous phase transition, and this is called a second order phase transition. In this case, unlike the first order phase transition, there is no hysteresis or latent heat. And in this case, we can characterize the transition, so in the vicinity of Tc, how this order parameter is changing by what's known as critical exponents. And in the vicinity of Tc, we call that the critical region. So I'm going to focus now primarily on second order phase transitions, which have this continuous change in the order parameter. Now, is there a simple way to theoretically describe these? And we can use mean field theory. It's probably the simplest thing to do at first. And the idea here is to write down a free energy for your system in terms of powers of your order parameter. And here, for a magnet, we'll have a term for having an applied field, and then we have other powers, and it's often the case that only the even powers will appear in this sum. For example, if up is no different than down, then you're not going to have the odd powers appear. So let's just keep low order terms, so you'll have this m squared term and an m to the fourth term in addition to the term in the magnetic field. And let's examine this for different values of this r parameter. So this is, the r parameter is just the factor in front of the m squared, and for positive r, you get this very simple parabolic-like shape, and it has a minimum at m equals 0. Now at the opposite sign, so we're going to keep this u as positive. So for the opposite sign of r, well, then you get this functional form, and if you see where the minima are, well, you get two minima now, and they are at non-zero values of m. So if you want to match this with a phase transition, well, then you can make the connection between R and the temperature, or the deviation of the temperature from Tc. So if we make this connection R equals some constant A times T minus Tc, then this is describing our continuous second order phase transition. And now, if you just take the free energy and you try to find where the minima are, and we also turn off our applied field, you get the following expression for the order parameter. As a function of temperature, it'll be 0 at temperatures greater than Tc, and it will have this dependence. You don't know what I'm looking at? Yeah, this dependence over here for temperatures less than Tc. And the main thing to note here is that you do have this collection of constants in front, but you have this expression T minus Tc to the 1/2 power, or the square root of T minus Tc. So this power 1/2 is our first critical exponent. It describes the rise of the order parameter below Tc. And this exponent comes from our simple mean field theory. So the exponents will depend on the type of calculation that you perform that best describes that system. Okay, so let's continue a little bit more in Landau mean field theory. So we can derive some other relationships. So this top relationship again comes from just minimizing this free energy. You essentially get an equation of state. And from this relationship at T equals Tc, you get a relationship between the order parameter at Tc and H. And it has this 1/3 exponent here. You can also calculate a susceptibility, and in this case, it's more easy to calculate the inverse of the susceptibility as dH dm, and let's evaluate it at H equals to 0, and you get this expression here, which when you invert it to get the susceptibility, you get the following. The susceptibility equals 1 over some constant T minus Tc for T greater than Tc, and you get this expression with the negative sign 1 over 2a T minus Tc, and this quantity is still positive because Tc is now less than Tc. And if you plot this, you get the cartoon that I show at the bottom, that the susceptibility as a function of temperature, as you approach the transition temperature from above, you get this apparent divergence in the susceptibility. And as well, if you approach Tc from below, increasing the temperature, you get this divergence of the susceptibility. And mean field theory tells you what the exponent is for that divergence. You see that the power for the T minus Tc down here is just 1. And you actually have an asymmetry in the amplitudes from the positive side and the negative side, and that's also shown here by these prefactors. So we've seen from Landau theory that there are exponents that characterize some observable quantities near these phase transitions. And just as a summary, and the what's the word? The jargon, or the symbols that we use for these exponents. For the order parameter as a function of temperature, that exponent we will use beta. For the order parameter as a function of field, we have this delta exponent. For the susceptibility, its divergence as a function of temperature, we'll use gamma. And in this case, we can define a susceptibility plus and minus, which is as you approach Tc from above or below. In principle, you may get different exponents. So there's this this gamma plus and gamma minus. There's also exponents for the specific heat, and again from approaching Tc from above or below, and we'll use alpha for that. And there's a critical exponent associated with the correlation length. And again, this depends on if you're approaching from above or below, and we'll use nu for that exponent. And let's see. Let's talk a little bit more about spatial correlations next. Oh, and another thing I wanted to mention is that neutrons can directly measure a lot of these quantities, such as the order parameter. Neutrons can directly measure. This order parameter is going to be related to the intensity of the Bragg peaks, the susceptibility, the spin fluctuations essentially are something that neutrons clearly can measure, and your neutrons have the spatial resolution to measure correlation lengths for these fluctuations. So neutrons are perhaps one of the most powerful probes of critical phenomena. Okay, so how do we get information on the spatial correlations? Again, in previous lectures, you've talked about how the neutron cross-section is related to the correlation functions. And what we'll consider here is if you do a neutron experiment and you don't resolve the energy, or in other words, you integrate over energy, and what we'll measure is this S of Q. So this S of Q is taking the dynamic structure factor S of Q comma omega, and you integrate over omega. And what this gives you is a spin-spin correlation function. But since you've integrated over omega, this is the equal time pair correlation function. Another way to think about this is that if you just take a snapshot of your system, so it's some instantaneous picture of the correlations in your system when you're in some thermal equilibrium state. So this quantity S of Q is going to be of interest when we want to characterize the critical fluctuations. Now we can relate the S of Q quantity with the response function, the susceptibility. And I had talked about the susceptibility just on a previous slide. And this comes from essentially the fluctuation dissipation theorem, where you can integrate over energy, and you get this result, and it's essentially the classical result for this. So a very simple relationship between what we measure with neutron scattering and a fundamental response function. Now, how can you get some Q dependence to the response function? And what you will do there is you would add another term to your Landau free energy. And in this case, you will add a gradient term in order to get some spatial dependence. So, without doing all the math, but if you put in this gradient term, you write it out to second order, this yields harmonic fluctuations in the order parameter. And you can get an expression for your susceptibility that goes as the following. You have, this is the correlation length, c squared, over 1 plus q times c quantity squared. So this has a Lorentzian form as a function of wave vector. And this was the form proposed by Ornstein and Zernicke. This corresponds to having exponential decays in real space in 3 dimensions for your fluctuations above Tc. And there is another exponent that is commonly discussed, and this will be the last one that I'll bring up. It's if you look at S of Q at Tc, then at Tc you get these power law-like decays in Q, and this eta exponent is associated with that. Okay. So bear with me. I know this is a lot of just background before we do any neutron scattering, but let's get this out of the way. the basic idea now, instead of just using mean field theory, which clearly is not going to work on a lot of real systems, let's think about near the critical point. Then if you can make an assumption that the correlation length, C, is the only relevant length scale, then you can claim that the critical behavior is dominated by fluctuations that are self-similar up to that scale C. And with that idea, there's a technique called the renormalization group that can be employed to describe the critical phenomenon. And this has been used by many people. A Nobel Prize was given to Ken Wilson in 1982 for his theoretical work in this regard. And what comes out of this is that there's this idea of universality, that many different condensed matter systems that may not seem obviously related at all, such as having the magnets that some of us really love, but other people love soft condensed matter, and that's fine too, such as liquids or liquid crystals. They look very different, but close to a phase transition, they can be described by the same critical exponent if they have some certain commonalities, and there's this idea if they are near or if they go to the same renormalization group fixed point, then you'll get the same critical behavior. So the ingredients that go into that idea of having a universality class where these materials behave the same near the transition is if they have similar or the same spatial dimensions and the same symmetry of the order parameter, and typically we'll talk about having interaction potentials that are short-ranged. Okay. So again, the magnets that I'm going to talk about aren't the physics that you see aren't just particular to these particular magnets, but they will apply to other materials with similar dimensionality and symmetry of the order parameter. And let me just recall some results from a previous lecture that I gave. One was the Merman-Wagner theorem, which said that if you have a continuous symmetry, so the order parameter has continuous symmetry, then you do not have a finite temperature phase transition if the dimension of your system is 2 dimensions or less. So for Heisenberg model systems or XY model systems where you have a continuous symmetry, then you need to have 3-dimensional materials with interactions in these 3 dimensions to give you a phase transition. Now, you can have phase transitions in 2 dimensions if you have a discrete order parameter. And an example, a quite famous example of that is the 2D Ising model. So where the spins are constrained to be either up or down, then there is an exact solution, and Onsager had this first went over that, and you can calculate the exponents in that model. The exponents, these are the exact exponents, are alpha equals 0, beta equals 1/8, and again beta is the exponent that goes with the order parameter, and gamma equals 7/4 for the susceptibility. And I guess this beta of 1/8 is something to keep in mind because we're going to see that in some neutron experiments. Okay, and so now there's been a lot of theory for different systems, and here's a table. You can make a table of different exponents. So let's just look at these 3D theories, and if you have, so n is the number of components in your order parameter. So 1 would be Ising, 2 would be XY, and 3 would be Heisenberg. And you can calculate the exponents alpha, beta, gamma, nu, and eta. So again, beta is something I think it's more familiar to a lot of us. It's the exponent for the order parameter. And if you look at these different 3D theories, beta is not changing too much. It's always close to 1/3. And it's also pretty much true for gamma. These don't change very much. I got this table from the Chaikin and Lubensky textbook that might be familiar to many of you. And if you look down here, they claim some exponents from experiment, and here are some different three-dimensional systems, and the betas that they get there actually look very close to what you expect in 3 dimensions from theory. And same with gammas as well. Something that I would note down here is this last line. It's 2D with n equals 1. So that's the 2D Ising model. And they claim that some of the betas in the experiments are, again, close to 0.3. And I'm actually kind of confused in where they get that from. They claim on the bottom here experiments in 2D n equals 1 compiled from some anti-ferromagnetic transitions. This clearly does not follow what's expected for the 2D Ising model. I said that should be 1/8, which is closer to 0.125. So there are actually better experiments. They probably looked at the wrong papers, perhaps, that give you exponents that are closer to what we expect. Okay, so let me go through a nice, I'll call it a classic neutron scattering study of critical behavior. And this will be focused on a 2-dimensional magnet. And this work was done by Bergeneau and Shirani and co-workers. Here's one of the papers from 1977 that I've taken a lot of figures from, but there's also some other work that I just list over here. And let me just focus on one of the systems that they studied, this material K2NiF4. The basic idea in this crystal structure is that you have magnetic nickel ions. In this case, it's spin 1. And they form a square lattice. So you can see this top plane up here has magnetic nickel ions, and you actually see the moments drawn in. Then there's another plane in the middle of nickel ions, and then another plane on the bottom. And there are strong couplings between nickel ions in the plane, but there's this large space in between layers, so they are very weakly coupled between layers. And you can see that there is a slight preference in the direction for the ordering. It's shown here to have this up-down type of ordering. So the preferred spin direction for the sublattice is along the C direction. So something to keep in mind is that the C direction is the long axis of this crystal material, and it's a tetragonal crystal structure. Okay, so there's very weak coupling along the C direction, but in the A and B direction, there are stronger couplings, and that's the predominant magnetic exchange. And shown here to the left is the reciprocal space for this crystal. This is just the AC plane. So you'll see Bragg peak, I guess shown in the open circles at 002, and the magnetic reciprocal lattice positions are given by the black dots, and I'll discuss more of that next. So I'll come back to this diagram. All right, but let me say a few more words about the Hamiltonian. So again, here's the crystal structure. They use this Heisenberg Hamiltonian with this additional term, and this is the additional term that's effectively giving you the Ising anisotropy. They're just placing some anisotropy field, this H superscript A is the anisotropy field, that gives you a slight preference for spins pointing in the Z direction. And they can write this as a reduced anisotropy energy, and the parameters for this material, so K2NiF4, we'll just pay attention to this top line here. You have J nearest neighbor in plane of 104 Kelvin, spin 1. This anisotropy ratio is very small, but it's not 0, so it's 0.002 roughly. And there is an ordering temperature, so this is where you have three-dimensional antiferromagnetism of about 97 Kelvin. Okay, so that's the basics for the energy in the spin Hamiltonian. And so what things can you measure? So something that is often measured first is to see if there is magnetic ordering at low temperatures, and there you just want to see if you have magnetic Bragg peaks. And in the case of an antiferromagnet, you would get additional sharp Bragg peaks at low temperatures, and they will appear at certain centers of the magnetic Brillouin zones. And what's plotted on this upper panel is the intensity at one of these Bragg positions, the magnetic Bragg peak positions, and up here it's at the 100 position, and you see that below this Tn, again it's around 97 Kelvin, you have this upturn in the Bragg intensity for the scattering. So the Bragg intensity tells us about the order parameter here. And in particular, since what we're measuring are related to pair correlation functions, we're measuring m squared, the order parameter squared. So the power law for the intensity will have an exponent of 2 beta. So just by measuring this intensity as a function of temperature, that gives us a measure of one of these exponents, the critical exponents. And you can see that this transition looks very sharp in the sense that this has a very almost vertical slope when it onsets. And that goes hand in hand with having a small value for the exponent. And 1/8 in the Ising model is a very small value. So this exponent is consistent with the two-dimensional Ising exponent. And in particular, down here in this table, they list the exponents that they extract from their measurements, and beta here is 0.14. So that's close to 1/8. And again, that's for this three-dimensional magnetic Bragg scattering. And I'll talk about this lower panel a little bit later, but just so you can see, you might have been staring at it. This is not at a Bragg position. This is slightly off a Bragg position, but there's a rod of scattering that occurs, which I'll discuss a little bit more. And you see these apparent divergences of the intensity as you approach this critical temperature on cooling, and then here on warming. Let me come back to that in a second. So, some things that we can note, that the magnetic Bragg peaks, they are definitely three-dimensional Bragg peaks. They're essentially delta functions in the 3q directions. And by measuring their intensity, we can get the 2D Ising model exponent. So that tells us that the critical behavior is two-dimensional. And that seems maybe a little surprising at first. We're measuring 3D Bragg peaks, but we're getting 2D critical behavior. And in this case, that's telling us that two-dimensional fluctuations dominate the critical behavior. So in fact, this is not so unexpected, and maybe if you thought about it, this is expected. That if you looked at the Hamiltonian, we were claiming that this in-plane exchange is the dominant term in the spin Hamiltonian. It's a 2D interacting system with very weak coupling between planes. Now it is true that the weak coupling between planes is not 0 because it does order into a three-dimensional pattern, but it could be the case where the three-dimensional, so there should be a three-dimensional critical regime associated with the 3D ordering. But this critical regime could be very narrow to be experimentally inaccessible. And that's probably what's going on here. But the 2D critical fluctuations a little bit further from Tn persist in a measurable way over a much wider temperature range. And then that is what we'll be measuring, for example, in the power law of the order parameter below Tn. So can we ask now, how can we more directly measure the two-dimensional fluctuations? And there is a very nice way of doing that, and it's when you think about the fluctuations. So let's say you're slightly above Tn, so you're not ordered yet, but you do have fluctuations. You do have these correlated regions that are growing in size as you cool down. And these correlated regions are fluctuating, so they're not static yet, but you will get scattering from those correlated regions. And their correlations, the spin-spin correlations, exist in the plane, not between planes. So what we get from that, from these 2D spin correlations, are rods of scattering in reciprocal space. And if you just think about it, if you have 2D real space correlations and you just Fourier transform those correlations, you should get rods of scattering. And what does that mean? Well, it's telling you that the narrow directions through the rods correspond to your two in-plane directions. So where you do have significant real space correlations, you'll get your narrow width in reciprocal space. But now you have this third direction where your spins are essentially uncoupled. They're uncorrelated between planes. So if they're uncorrelated between planes, then you'll get essentially this extremely broad scattering in the form of a rod, and the rod in reciprocal space is shown here as this shaded hatched region. And as I said, that is the C direction. So that's in reciprocal space, the C star direction. The rod is parallel to the C star direction. So when you want to now measure 2D fluctuations, we can fit the susceptibility with this Ornstein-Zernicke form, and the width of this rod is inversely proportional to the correlation length C. So we'll be getting the 2D correlation length. Okay, so that's very nice. Okay, so that seems very nice, just in principle, that we can just go ahead and measure the 2D correlations, but there is an experimental challenge to be overcome here. And again, here is the static structure factor when we integrate over all frequencies. And this integral here is technically from -infinity to infinity to get this equal time correlation function. So what we want to do is to perform this integral experimentally, integrating over a large relevant energy range. And so it's not going to be from -infinity to infinity, but it would be, you hope it to be over a large range compared to the energies of relevance in your system. And when you're close to a phase transition, you do get, you're mostly dominated by lower energy behavior, but you would hope to integrate over, say, a range of J or multiples of J. So how can we integrate over a large energy range without having resolution effects mess up this experimental integration? That is, how can we do this energy integration without integrating over Q? And you should recall that for neutron spectrometers, you do have these resolution functions. For a triple axis spectrometer, it's in the shape of an ellipse. And this ellipse is an ellipse in the four-dimensional momentum and omega space. and it has a slope in that space, and that comes from the fact that the energy transfer and momentum transfer are coupled. So it's going to be hard for us just to integrate over energy without simultaneously integrating over some range in wave vector. So that's an experimental challenge. Now, other probes can do this more simply. X-ray diffraction, for example, this is not an issue. You essentially automatically integrate over energy, and that's because X-rays or photons have a very different dispersion relation than neutrons do. And since the dispersion for the photons are so steep compared to magnetic spin wave dispersions or phonon dispersions, that you have a very broad energy resolution, and you're essentially integrating over energy, maintaining a good Q resolution. But that's not going to be the case for neutrons, which their dispersions are much closer to those in solid-state systems. So there's a very nice trick, we can call it a trick, or some insight that was exploited by the co-workers Bergeneau, Sharani et al. To overcome this challenge experimentally, and we'll call it the quasi-elastic approximation. And this works because we have this two-dimensional system, so it's a low-dimensional magnetic system. And here's the basic idea. So the basic idea is to exploit the fact that the cross-section is independent of QZ. So this is the component of Q that's along the C direction. So we said that you get these rods of scattering along C star, so the cross-section is independent of that C star direction, and I call that Z as well here. So if we can exploit the fact that the cross-section is independent of this direction along the rod, so we're free to choose the Q position along the rod through which we want to do our measurements, and let's use that choice intelligently. So if we choose Q to be someplace on the rod such that KF, so this is the scattered neutron direction or wave vector, and we want that direction to be parallel with the rod. And that's shown in this diagram up here. So this red arrow is the Q vector, and let's choose it to be somewhere on this shaded rod as shown here. And with that choice, if you look at the scattering triangle, KF turns out to be now parallel with this rod direction. And that is a very nice choice. So what does that mean? So if that's the case, when we do a two-axis measurement, so we are not using an analyzer crystal, so there's no energy analysis, we just have a detector, and any neutron hitting the detector is counted. So every scattered neutron hitting that detector now has the same Q in plane. And this does take a little bit, if you haven't thought about this before, a little bit of time to sink in. And going up here again, what you can see is if you change the length of this KF that I'm pointing to, right, so KI over here is fixed. So KF here, changing that changes your overall Q, but the way it changes Q is that it will move Q along, yeah, it's hard to, I'm trying to move this arrow around. It'll move your Q all around different positions, such as here, parallel to this rod. So QZ will change if QZ will change if KF changes. So by measuring various KFs in a fixed spectrometer position, you are integrating over many final energies. You're also integrating over many Qs because, again, they are coupled. However, you are not changing the in-plane Q. That is, you're not changing the Q perpendicular to this rod, you're only changing the Q along the rod. So that's the basic idea. So that's the upshot. You can integrate over energy without changing Q in plane. And that's what we want to do a proper energy integration and to be able to measure the instantaneous correlations. Okay. So I'll just say a few more words about these experimental aspects. One thing that you see when you do an experiment is you can just physically check the c-axis. So this is the direction perpendicular to the planes of your sample. You know, if you carefully mark that on your cryostat or whatever sample environment you have, that direction better be pointing directly toward the detector, right? That's just another way of talking about this fancy geometry. So you choose the specific Q on the rod to do a measurement at such that the c-axis points directly at your detector, meaning all the various kf's just change components of Q along C. Then what you typically want to do then is use tight collimations. So this will give you good Q resolution because if you want to measure divergent correlation lengths, you want to have very good Q resolution. And one thing to keep in mind is that the energy integration is not to infinity. It will be cut off as high as your incident energy. So you might try doing measurements at various incident energies to see if you get the same results, meaning that you are doing a good relevant energy integration. So here's some results from the Bergeneau et al. Group. And this is the intensity along the rod direction. And there's a very broad peak here. And the reason that you see this broad peak is the peak is a maximum at this special Q vector over here that you want to sit at for your measurements. So that is satisfying this quasi-elastic approximation. And you get the most intensity, which is nice, because you're effectively integrating over all of the energies that are hitting your detector without changing Q. If you're on a part of the rod away from that ideal position, your intensity decreases, but it won't go to zero because you still have, you know, the scattering along that rod. But now when you integrate over energy, you're also changing Q in plane, and because you will have some dispersion of your excitations along the in-plane direction, you get a diminishment in the peak intensity there, and that's what this is showing. So this is one way to know that you're at the ideal Q, is if you can spend time to do a scan like this, then you want to be seated right at where this arrow is. But again, it's something that you can just calculate. You want to be at the Q where the c-axis points to the detector. Okay, so let's look at some data, some more data. So here's some scans just along the rod, and here it's not as obvious that there is this maximum, but these white open symbols are scattering from the rod, and it has this weak dependence on this L or C star direction. And you also get these Bragg peaks that are quite sharp here and here. Now, if you scan through the rod, you get peaks that are very sharp. So they should go from background, and you'll go through the rod, get a lot of magnetic scattering, and then go back down to background. So those are scans through the rod. And so here are some more scans through the rod, and the analysis has some subtleties to it. One thing that we have to note is what you're seeing again is a 2D Ising-critical phenomenon. So it's going to be only the component along this easy axis direction that has the 2D Ising criticality. So therefore, only fluctuations up and down in this out-of-plane direction will have this divergence, for example, in the susceptibility according to the Ising model, but the fluctuations in the plane are related to having the Heisenberg spin components remaining, and they do not diverge at Tc, or Tn in this case. So you want to differentiate, and that's what's shown here in the cross-section, between the spin fluctuations that are perpendicular to the c direction and the spin fluctuations that are along the c direction. And the nice thing is, and we've discussed this before, the neutron cross-section also has this orientation factor due to the dipole interaction of the neutron with the moment, and that's one way to distinguish, or to help distinguish this. But if you're now choose a specific Q position to sit at, then these orientation factors are determined by where you are sitting. And it turns out if you sit at the Q position shown with this red arrow up here, these orientation factors are roughly equal to each other again, these are the fluctuations perpendicular to the planes and parallel to the plane. Perpendicular to C and parallel to C. All right. So some of the data shown here, so the black data are taken very close to Tn, and this is where you expect the divergence in the susceptibility. So you should get much enhanced signal, and that's seen there. At temperatures substantially below Tn, so at 90 Kelvin, you see the open symbols, so it's much weaker, and this is primarily the transverse fluctuations that are measured. And that's because the black filled symbols, you have this divergence due to the longitudinal part that's along this Ising EZ axis direction. But as you cool down below Tn, that susceptibility should die off very quickly like a power law. And when you're at 90 Kelvin, you're just left with the transverse fluctuations. And you can think of the open symbols as scattering from spin waves, but since we're not doing an energy resolve measurement, you just think about having a spin wave dispersion, and then you integrate over the low Q region, and you'll get some intensity that's peaked, something like that. And that's how they do their analysis. So they want to be able to separate the transverse fluctuations from the longitudinal fluctuations that have Ising criticality. Okay, so here is just some raw data. Here's the intensity divided by temperature, and this is going to be the sum of the transverse and longitudinal susceptibilities, just because of the way the orientation factors work out at this Q vector. And you see that you have this upturn of the susceptibility as you cool down, and then it drops down as you go below Tn. And here's the width of the scattering through the rod, and you see that the width diminishes, so you get a very sharp peak as you get close to Tn, and then it broadens again below Tn. Okay, so now they can do a more in-depth analysis. So they're going to fit the data with essentially the Ornstein-Zernicke form, these Lorentzians, and they'll take into account the instrumental resolution, and they'll take into account the two directions for the fluctuations, along the c direction and perpendicular to the c direction. And when they do this analysis, they can extract separately the longitudinal susceptibility and the transverse susceptibility. And it's the longitudinal susceptibility that they now plot as the filled symbols. And that is the part that should have this Ising criticality and have the divergence as you cool down. That's clearly seen, and the divergence as you approach from below. And there's also clearly this asymmetry in the prefactors for these divergences as we've seen in Landau theory, but now this is more closely following the 2D Ising model. Let's see. Over here, several different materials are plotted, but yeah, this bottom line and the data associated with that are as a function of t over tn minus 1. This is kappa longitudinal, that's the width of the peak in the in-plane direction. And as a function of temperature, if you plot this on a log-log scale, you see that it's a line, which means that there's a power law, and the line is, the solid line is the 2D Ising model expectation. So that seems to work quite nicely. And so that was the width. You can look at the intensity. So they plot here T times the susceptibility at the 100 position, this Bragg position, and as a function of temperature, or the deviation from Tn. And they see that this also follows a power law. So you do have a power law in the susceptibility, so you can get gamma from that. That's for above Tn, and then for below Tn is shown in this panel. They have an extraction of gamma below Tn 1.75, an extraction of nu, the critical correlation length exponent, of 1, and these are consistent with the 2D Ising model. So summarizing, these really classic experiments on K2NIF4, that this is, I can't say it any better than the way they say it in their paper. So they measure a reduced temperature range from 0.15 to 0.008, so they're getting very close to Tn. And they can measure correlation lengths ranging from 20 to 250 lattice units. And what cuts off this high value for the correlation length is just instrumental resolution effects. And what they can see quite nicely is that the critical phenomenon is dominated by 2D Ising physics. And this is clearly two-dimensional physics, first and foremost, and the particular values are Ising-like. So I hope you could see from this the power of neutron scattering for testing these fundamental ideas in critical phenomenon. And this is a case study of something that we kind of expected, but it's always good to learn from doing measurements of things that we know what they should be, and having the precision in your experiments to bear that out. So as one final system before wrapping up, this is related to the previous system. It's a square lattice antiferromagnet. And I can't help just going from things that I know. I actually did this as probably my first experiment as a graduate student. And we studied rubidium manganese fluoride, which has a larger spin, 5/2, on the square lattice Heisenberg antiferromagnet. This also has a small Ising anisotropy term, just like K2NIF4. And what we wanted to do here was to measure the crossover, or to just understand better the crossover from Heisenberg behavior to the Ising behavior. And in particular, due to the Merman-Wagner theorem, the Heisenberg fluctuations will not be divergent at Tn, right? Only the Ising-like fluctuations would. So we want to see, can we measure the Heisenberg-like critical phenomenon and then match that with theory, which is much harder to do for just the Heisenberg fluctuations. And here's some representative data. So we have measured with two different incident energies of 41 millivolts and 14 millivolts. Let's see, the Tn for this material is, I forget, roughly 40 Kelvin. Memory down back to 1998 isn't so great. All right, but so here's a wide temperature range above Tn. You can see that you have very broad peaks, and these are now choosing the special Q to give us this quasi-elastic approximation accurately. So we see broad peaks that are narrowing, sharpening up as you cool down, and with different incident energy, you do a different energy integration cutoff, and we also see the peak sharpening as you cool down. I show you the resolution here. It's very narrow compared to the width of the peaks. And another thing that I show is we also have this issue of the longitudinal fluctuations versus the transverse fluctuations. The longitudinal fluctuations are Ising-like, they diverge. The transverse component does not diverge. And here's a sense of the contributions of each. So here's a transverse component here, and it's a longitudinal part that is very sharp and divergent, and it's more clearly seen down here. Now, if you do the analysis and you separate the longitudinal from the transverse components, let's look at the longitudinal component over a wide range of temperature above Tn. So when you're close to Tn, it's true that the Ising fluctuations dominate, but once you get to, let's say, 20% above Tn, so roughly 50 K and higher, you should be dominated by Heisenberg fluctuations. You're no longer in the Ising critical regime. So at these high temperatures, you are looking at the 2D Heisenberg model and how those fluctuations change with temperature. And that is still a very interesting question to be addressed with theory, and there is some nice progress being made. So some things you can do are series expansion calculations, and this other thing, PQSCHA, I think it's a purely quantum self-consistent harmonic approximation. And it's just an approximation for how the critical behavior should behave, taking into account the spin 5 halves here. So it's very close to being classical behavior with small quantum corrections. So here is how S of Q at the anti-ferromagnetic wave vector S of Q equals 0 behaves, and you have this upturn. And again, you don't get the divergence in these calculations because what we're looking at is the Heisenberg critical behavior, so that should keep going up all the way down to 0 temperature. And over here is the correlation length as a function of, and this is plotted in 1 over temperature. So what you see is as you go down in temperature, so it means going to the right here, the correlation lengths increase, and you don't get a divergence at Tn again because, at least in some of these theory lines, because we're trying to compare to the Heisenberg behavior. So at high temperatures down here, the data seem to match very well with the Heisenberg model, but clearly at some point the Ising behavior starts to kick in. And the best thing that we can try is to take one of these Heisenberg calculations, so such as this long dashed line here, add the Ising anisotropy, and that kind of captures the behavior. You get near Tn some Ising-like divergence, but away from Tn it follows some Heisenberg behavior. So these are comparisons with no adjustable parameters to models of just the square lattice Heisenberg model. And what we're seeing, the main conclusion is this is consistent with classical scaling, which is to be expected because spin 5 halves is a relatively large spin, which is close to classical. You can ask the question, if you have spin 1 half, what type of scaling you should get. and I'll leave that the subject for the future lecture when quantum behavior might be important, and you might get something that's not just classical behavior, or maybe not. We'll see. All right. So that was it for this lecture. The summary: neutron scattering is a unique and I'd say very powerful probe of critical phenomenon. You can directly measure several of the quantities related to the critical fluctuations and measure several of the critical exponents. And I spent a lot of time doing a case study of two-dimensional magnet, in particular the square lattice K2NIF4, and one of the experimental methods used allowed us to do a very good quasi-elastic approximation and energy integration on the spectrometer to extract S of Q. Okay, that's it for today. And I guess I could open this up for questions. Okay, there's a question. How does one measure S of Q for 3D materials? There's going to be some issues there with the fact that when you start integrating over energy, you're also changing your Q vector. It's hard to do an energy integration sitting at a specific Q. So you have to model that, I guess, and take that into account when you do your analysis. So you don't have this nice trick of aligning KF along your rod of scattering. So I would say that there are some more difficulties there associated with that. But you still, maybe a small energy integration depending on the size of your energy scale is enough, and then it doesn't change your Q very much, and maybe you'll be happy with that. It'll be materials dependent at some level as well about how much of an issue this is.